Okay, so some people ask me on other school that we show how to make crystals, and we had this very small movie, but it has to start from the beginning. Okay, so you take polycrystalline samples, and then you put it in a gradient, temperature gradient, with some iodide, and here you see how the polycrystalline sample shrinks, and I hope you see the single crystal here growing. And it grows, and at a certain point you should stop, because sometimes you have problems and it reacts with a wall, what you see here. But you see, this is not so difficult, and it gives you maybe a little bit of feeling, now it goes back, how we grow many of the single crystals. There are different methods to make single crystals, but this is simply one for many of the single crystals where we use this chemical transport reaction. Okay, good. So in my first part, I talked about how to get the materials, and yet now I want to take the magnetic wide semimetals, because this is a very interesting topic nowadays to explain you how to measure the materials. Here is all about bike and the first approximation, and so as I said, you have already an impression now even how to find the materials, but how to measure. And most of our measurements are classical measurements, so different from what you heard, so about the quantum spin Hall system, mercury telluride already. So we measure bike materials, so we measure the Hall effect, so we measure the transport by applying a magnetic field, and we get information like the mobility, the charge carrier type, etc. But if we have magnetic material, if they are paramagnetic, and Stuart will talk about this, you can also measure the spin Hall effect, and this is strongly in this paramagnetic material related to the barrier curvature. And if you have a magnetic material, you have an additional contribution to the Hall effect due to the magnetic moment of the material, and you measure the anomalous Hall effect. And all this classical measurement has their quantum analogs. So you heard about the quantum Hall effect, where you see the topological edge state in a big magnetic field. And at low temperature, like von Klitzing invented, but in graphene you can measure this in a big magnetic field, even at higher temperature. And you learned about the quantum spin Hall effect. Because of topology, we don't need the magnetic field. And the quantum anomalous Hall effect, because of the intrinsic magnetic field of the magnetic material, one of this topological currents, spin currents, is suppressed, and this would be the dream of Stuart, to have a spintronic material where you really have one spin. But as you can imagine, all this effect would be nice to have at room temperature. Many, like the quantum anomalous Hall effect, also this effect can be also useful in future quantum computing, and always it would be nice to have it not at 20 millikelvin, so therefore you need people like me and Leslie, for example, to find new materials. Okay, so then you can also measure what we do. Instead of having a current, you apply a thermal gradient, and you can measure Seebeck and Nernst effect. And the anomalous Hall effect, there's an anomalous Nernst effect, which is strongly related against with the barrier curvature, and so you will find Noki here in the audience, who does high throughput calculation on anomalous Nernst effect of many material. So there might be even some classical, despite of spintronic, some other classical application for the material, because based on the design of the barrier curvature in topological materials, this Nernst effect and this Seebeck effect can be much larger than what you expect. And normally we are limited by the Wiedemann-Franz law, so the conductivity is connected to the Seebeck effect in an unpleasant way, so therefore we cannot gain really enough energy to make it an application, but here we might have a way to really go. And I simply want to mention this very nice article from Otto Naragosa about the anomalous Hall effect, and there's also a lot about spin Hall effect. So I think where he nicely wrote together with Onk and others and Gyros-Nova, how the barrier curvature and this Hall effects are connected. And you nicely see already, if you see this here, the spin Hall effect of platinum. So here as a function of the energy, that especially if you have crossing points in the band structure, and platinum is a material with the element with the highest spin Hall effect, and I hope you hear more about this elements. Okay. So I want to talk also about Y semi-metals because they seem to have, if you have the Y point at the Fermi energy and magnetic Y semi-metals, they seem to have very large Berry curvatures. And so we have heard a lot already. I think I don't have to discuss it in detail, but I will remind you. So we have this overlap of the conduction and the valence band, which we call in chemistry inert pair effect, which leads to this, even if you look in 3-dimensional, an overlapping area. So, and if this crossing area opens up, we have a topological insulator with this very nice Dirac cone surface state, and we heard a lot in the previous talk what kind of measurements you can do and even get more information out of this. What can happen is that this area doesn't open up completely, and you have these touching points left over, which can be Dirac points or Y semi-metal depending from where they are. So, and what the symmetry of the material is. So if they are at high symmetry points, and you have, so you have, like in graphene, you have these Dirac points which are 4 times degenerated. So you were already discussing the degeneration, I assume, from the Dirac point in comparison with the mercury telluride. And then if you apply magnetic field, or if you reduce the symmetry of the material, if you remove inversion symmetry, for example, you can split Dirac points into Y points in the bike, so they have a certain chirality now. It's based, you learned about already Berry curvature and magnetic monopoles, which leads then to certain transport properties and Chern numbers here, and also to surface states which are now Fermi arcs, which are connected on the different sides of my single crystal. So we are looking for magnetic Y semi-metals because you can break the inversion symmetry, but you can also break the time reversal symmetry. And if I have a magnetic crystal, I always have broken time reversal symmetry. Now you can imagine we simply have to look for these points, crossing points in magnetic materials at the Fermi energy. So this is simply what I said already here. You have your Dirac point. You can split it into Y points by breaking the symmetry or time reversal symmetry, and you can, the first feature we are looking for is Fermi arcs, which you can see in Engelrut's photo emission, what was also mentioned today, or maybe in STM, and you will hear in the coming week about STM measurement from Heim. Okay, so, but life is always a little bit more complicated than you think on the first view. So this is a band structure of graphene, which you saw already in the morning. It's a very nice broad energy range here, about 50 eV. So because of the strong carbon-carbon bonding, you have very wide bands. And you see there are not so many bands around the Fermi energy, so you really have this Dirac point at the Fermi energy, nothing else. Which is a very nice type 1 Dirac point, and the Fermi energy, if the Fermi energy is just there's just a point. But in reality, we very often see that this is not the case because you have more bands around the Fermi energy, and the Dirac cone, for example, can be tilted, which leads to electron and hole pockets. And for me, I think, which I thought first was a disadvantage, might be an advantage, because my feeling is in graphene we have a very special situation with the delocalization with the aromatic electrons, why this can never open up this band gap because this costs really a lot of energy. But in other systems there might be charge density wave instabilities which allow to open up the band gap, and sometimes I have the feeling it's not so bad to have these additional bands around the Fermi energy, even if they maybe makes trouble if you have to argue with the referees, no? Because then they say everything comes from here and not from there. Okay, but I think it stabilizes, and I think, so one of the predicted systems like the iridates was recently also shown to be a charge density wave, and if they get rid of the charge density wave by sliding, they see the wild physics again. So this is a very famous system and might be the reason. So then theory predicts a series of interesting properties which are related to the chiral anomaly in some sense. So if you apply magnetic field, if you do now Hall measurements in like I described before, but depending from the direction now of my current and the magnetic field, I can have different results, which is surprising if you have a cubic system, but this is due to the chiral anomaly. So you have here your Landau levels, and you can maybe if the current and the magnetic field is in parallel, you can move density from here to there, which makes an asymmetry, and I think Atlan talked about this also already in some sense. So, and this leads to certain properties. From my simple viewpoint as an experimentalist, you can think suddenly this material in this certain situation behaves more like a magnetic system, even if the white semimetal is not magnetic, and it shows a negative magnetoresistance, which we know from magnetic system, but then in all the direction, and it shows also an anomalous Hall effect, which you would not expect in a non-magnetic system. So these are already additional features we can look for. The intrinsic anomalous Hall effect was found in a few systems, but there's also connected to this chiral anomaly planar Hall effect, and there was a prediction of the gravitational anomaly. This is only a similarity which was predicted in theory. So why do I like this chiral anomaly so much? So because this is like, even so my knowledge is not coming from quantum field theory, it comes from Wikipedia, so this is a reference. But it shows already how exciting this is. So you can see what we discussed already also at lunchtime. You can use condensed matter systems now for tabletop experiments in high energy physics. So in high energy physics, this was predicted here, this chiral anomaly, that you break the symmetry between antiparticles and particles. And this is a description which is this here in the Wikipedia. And you have an analogy between the Dirac semi-methods by having electrons and holes, and instead of the velocity is like the speed of light, it's for sure the Fermi velocity much smaller, but you can see many properties in analogy to this high energy experiment. So simply coming back to the chiral anomaly, so Johannes did very nice work on this in collaboration with us by making this niobium phosphide nanoribbon. And the nice thing is we always can exactly say where the Fermi energy is in this material, because these wiggles are here not noise. So they are quantum oscillation, and the quantum oscillations then can be compared with Jansson, who is also in the audience somewhere, his calculation. And from this we exactly know whether the Fermi energy is at the y point, because otherwise you would not see anything. So here accidentally we doped it with gallium because we made these wires and moved the Fermi energy to the right position, and then you see exactly what was predicted by the chiral anomaly. So the conductivity is proportional to B square if the current is perpendicular to the B field is perpendicular to the current, and positive, and it becomes negative if you have the magnetic field in direction of the current. But there was another prediction by Zubir Sachev, and he predicted if you apply instead of a current, if you do this, what I said, you can always do a temperature gradient, which we do also. So you should get a different behavior, which is related to this mixed axial gravitational anomaly. So you see a quadratic behavior at low fields, and it should diminish at high fields. So this was a prediction, and I show you how nicely does it compare with our measurements. This is the thermal gradient, this is the current, and the current goes with the B square, as you see nicely here. And the thermal gradient is first goes with B square, and then it diminishes, which was exactly what was predicted by the theory. And this is a nice thing for us. You know, we make the material, we measure something, you predict first, please. All the theoreticians, how many theoreticians are here? Nobody? More, no? I have hoped you are a theoretician, and I inspire you to predict more fast. Okay, good. So now we make the life a little bit more complicated, but you know, we were looking for these crossing points in the band structure, and there are different ways, and as I said, in magnetic systems, you can even find maybe more often this crossing point, because you get time reversal symmetry for free. But I again start with 1/2 Heusler compounds, which you learned about in this morning, simply because you can also simply, what you do if you take, for example, mercury telluride or a 1/2 Heusler compound, here we have the yttrium platinum bismuth, where you have these touching bands, And then in case of gadolinium, we have additional F electrons, but we don't need the magnetism in this material. This was inspired also by the work of, at the same time, when Hirschberger and André Bernowik for sure has published this nice paper. So you can turn this touching point even in a white semi-metal. And the nice thing is gadolinium platinum bismuth, you induce it in the field and you see really nearly everything so far. And I hope soon another member of the audience will publish a very nice, exciting paper also on gadolinium platinum bismuth. So here you see the B-square behavior we saw. We saw the chiral anomaly, and also Hirschberger saw this, and they saw interesting anomalous Seebeck effect. We saw an anomalous Hall effect and also the planar Hall effect. So we more or less can tack everything despite of the axial gravitational anomaly, which so far. But this is like you have a non-magnetic system and you induce wire by applying a magnetic field. So this is intrinsic in magnetic Heusler compounds, and we are interested in this class of material because it's also so nicely tunable. As I said, the half Heuslers are a little bit like stuffed zinc blender, like the mercury telluride, but you can also fill here the other tetrahedral site, and here you can do by keeping node central symmetry, so you can fill them with the same type of atoms which are sitting here, or you can fill them with the same type of atoms sitting here, and you have inversion symmetry. So here we can even play a little bit around with the symmetry and see, can we really see really topological difference if we have a mirror plane here in this plane or not? And you will see it's really possible. So similar like the electron counting you did for half Heuslers, you can do the same for the full Heuslers, and you have semiconductors for 8, 18, and 24 electrons here. So you can make an iron to vanadium aluminum compound which is non-magnetic. So this is related to these 4 atoms in the unit cell that you have 8, 18, and 24 valence electron non-magnetic semiconductors. So then if we put more electrons in the system, like for example 29 valence electrons like we have here in cobalt-2 manganese silicon, we can have a half metallic ferromagnet. This was my 24 electrons, one spin direction, other no magnetism. So if we put 5 more in one spin direction, we end up that this direction becomes metallic, and this is semiconducting, which is even a half metallic ferromagnet. And many of these compounds in the family of Heuslers are lying on this line, which are saying they're half metallic ferromagnets. But this is not the only interesting thing. These compounds of materials are ferromagnets with quite high transition temperature. As I told you, we want to have the quantum anomalous Hall effect at room temperature and not at 30 millikelvin. Okay? So we should have a magnetic system which is interesting in this regard, which has a higher TC. So we are looking, therefore, strongly for this magnetic system, which has higher TCs. And here you see the candidate materials are already good. And at this time, when we were working simply measuring Heusler compounds for totally other reasons to work with Stuart on spintronic, so André Bernowik and Hassan, they predicted here, I think Hassan passed by André's office anyway, so they predicted white semi-metals in Heusler compounds, which you nicely see here. This is at 0 is the Fermi energy. The crossing points are above the Fermi energy. But you see that in the spaghettis, in the band structures, there are many crossing points. But here it's nice because this is just one spin direction which is crossing the Fermi energy because this is a half metal. You know, this makes it so easy because in one spin direction we have no bands, we have anyway a gap. And in the other spin direction we have only this crossing bands. Okay? So we worked on this compound, cobalt-2 manganese aluminum, for a long time, and we already saw that we find a giant anomalous Hall effect. You remember you measured the Hall effect in this magnetic material in cobalt-2 manganese aluminum, and we were always surprised why. You know, now we know, because also here we have Y points, and here we just have it sitting at the Fermi energy, and from the calculation, it's a nice agreement with the measured one. So if you look, and this we did in 2012 without knowing, we recognized, okay, here's a cobalt-Heusler compound which is related very close to titanium tin. Here it's below the Fermi energy, the same crossing point, that there might be some relation with the Dirac cone in this material, because at a certain point people thought the anomalous Hall effect is directly related to the magnetization. And the nice thing is in the Heusler compound, since many are half metals, you simply increase the number of valence electrons, so you increase the number of magnetic moment. So you should increase the Hall effect. But this is not the case. If you see, there's no direct evidence that you constantly increase the Hall effect. You even can change sign, because it's, from our understanding, clearly related to the Berry curvature. And in this material, we really measure the intrinsic Berry curvature in this material. So here you see the Hall conductivity, which peaks, and the Y points in manganese to aluminum. Okay, so you can say, good, you see now there's very giant values in the Hall measurements, so what? And here you see nicely how you see. You saw already some Hall measurements before, but here you see nicely, you see how the anomalous Hall effect is different. So you see this jump, and it looks really like the magnetization curves here in the Hall measurement, and therefore the people thought at the beginning always it's like more goes with magnetization, but this is for sure not the case. And now you can calculate the Hall angle, which is the anomalous Hall effect divided more or less by the charge carrier concentration, to see how far you are from the quantum Hall effect, which anomalous Hall effect, which should be 1. And you see in this material it's quite high value, and I think finally this paper was unfortunately a little bit too early, was finally now accepted after many rounds in some journals at PRX. Anyway, so this 10% is already a high value. We will see even higher values as examples of us, and there was a paper this week also on a 2D ferromagnet, which has also 10% anomalous Hall effect. So this is something where people really are looking for in the moment, because this might be a system where we can look for quantum anomalous Hall effect. So as we already saw before, so without spin-orbit coupling, you have all these nodal lines, and if you apply spin-orbit coupling and a magnetic field in a certain direction, so this goes into this Y points. So we have also in this Heusler compounds quite some compounds which have gaps in both spin direction, which is surprising, because people looked for ferromagnetic semiconductors for many years. There were people very famous, but they always had to dope what the people do for the quantum anomalous Hall effect. Nowadays, they take a semiconductor and dope some magnetic ions in there. But then you have not really a real magnetic compound, you have a doped compound, you know. And the TCs they reached in gallium arsenide doped with manganese, like going up to 180 Kelvin, and then it's already metallic, and you know the low TCs from the bismuth doped compound. But in Heusler compound, you can have semiconductivity even in ferromagnet, and we thought always we called this because very often the gap is in one spin direction, very small spin gapless semiconductors, and in the context of Y physics now we understand, because they are strongly related to the Y, because now after also my lecture in the morning you understand, look, here's the cobalt-2 titanium tin, the compound Andre recommended for with Y points close to the Fermi energy, and you see here nicely the crossing point. So if you make now the same compound, not the same compound, the same number of valence electrons in a Heusler compound, only if you remove inversion symmetry, and this we can do, because this is a good thing here, we can tune this material. You know, we can play with this material, simply take another composition, but this has 26 valence electrons, this has 26 valence electrons, and you see, because you remove the inversion symmetry, you lose this crossing point, you lose the Y points. So this is very interesting. So via this we can explain, we have many numbers of valence electrons where we can design electronic structures like this, and we have many of this which always are related to Y points close to the Fermi energy. So then you can calculate the Berry curvature, and always if you lose this crossing point, the Berry curvature disappears, because now it's like, it's not a because the Berry curvature here, for example, if you compare now this cobalt to titanium tin, so if you have a mirror plane, so the Berry curvature is the same in the whole plane here. This is the plane where the mirror plane disappears, and here, if we have this spin gapless semiconductor where we don't have a mirror plane, So you see the Berry curvature can cancel. So here, therefore, we have a large value because there where we have the y points, the crossing point, they add all together up to a high value. But if we remove the mirror plane, so they can cancel, and the Berry curvature, the Anomalous Hall effect becomes 0. And this is interesting because this is what we like to do then, because to prove that this has nothing to do with the magnetization, we made a compound which has 26 valence electrons. So from the electron calculation rule, we know it should have 2 μ-Bohr. So you see here is the magnetization curve, 2 μ-Bohr, okay, per formula unit. And we made another compound which has also 2 μ-Bohr and has no mirror plane. So it has no inversion symmetry. And you see nicely how different the Anomalous Hall effect looks. So in the case where we have a mirror plane, it adds up. And you have a large Anomalous Hall effect. And if you have no mirror plane, it cancels. So symmetry counts. In the Anomalous Hall effect, there's nothing. You know, you don't see any jump here around the Fermi energy. So this was for me also very surprising. So you're always critical if you read something that this all should lead to so different properties. Anyway, but what Jansson and Jansang and Noki are doing, they do and look and optimize how we find compounds which has a large Anomalous Hall conductivity, but also have a large Anomalous Nernst effect. So because, as I said, this might be even give us access to high temperature or even give us access to new devices for energy conversion, what the Seebeck effect itself and thermoelectric doesn't achieve, because 2 is their limitation. So, and indeed, if you see, you have to believe me now, it's again cobalt 2 manganese gallium, which has this giant Anomalous Hall effect. It has also a very large Nernst effect. And you see, even if you see as a function of temperature, it's increasing. It's 6. So I will show you in comparison to other magnetic materials that this is really giant. But you see, since Tc is somewhere here at 800, it might go up to 10. Okay, so it's really much larger, more than an order of magnitude what we know from other magnetic materials. And at the time when we were publishing this on ContMat, slightly after us, there was another paper published on ContMat, also working on giant Anomalous Hall effect, which was now published in Nature Physics, face-to-face to another paper of us, but this is now still struggling. Anyway, what you see is simply here the Nernst effect as a function of the magnetization. And so in normal system, very often where you don't have nice crossing points in the Berry curvature, it really indeed looks like it goes with the magnetization in the first approximation if you don't look in detail, but you see this is quite a broad range what they allow for to say this is linear. But cobalt 2 manganese gallium really stands totally out because it's more than an order of magnitude larger. And there's another material that stands out, and this we worked on before. It's a manganese 3 tin, which is even an antiferromagnet, which has no moment at all. Okay, so I want to come now to this manganese 3 tin compound, which is a distorted Heusler compound, which is an antiferromagnet, a frustrated system. So, and how can we get more anisotropic material, which is also important for the quantum Anomalous Hall effect? You want to have out-of-plane magnetization. So it's good if you can slightly distort your crystal structure to give the magnetization a preferred orientation. And we can distort the Heuslers in 2 ways along the 1, 0, 0 direction. This is the so-called martensitic phase transition, which we have quite often in the shape memory alloys and magnetocaloric material. And we can distort it along the 1, 1, 1 direction. And then, you know, as I said, there's a relation between cubic and hexagonal. You come to a hexagonal structure. So in an antiferromagnet, we have really no Anomalous Hall effect. Here we take simply an antiferromagnetic Heusler. And you see here the Berry phases for both spin direction. And you see over the whole temperature range, energy range around the Fermi, everywhere it cancels out to 0. This is symmetry related. And so it was always like, okay, so we believed, okay, antiferromagnet, no magnetic moment has to be 0, this value have to be 0. So can we make antiferromagnets where this is not 0? Indeed, we can do this, and one example was here, manganese 3 tin. At the same time, we published this theoretically as Anne MacDonald published manganese 3 iridium. which is similar from the structure. So here you have this Heusler distorted, and all my spins are lying in plane, and they are antiferromagnetic arranged, they are chiral, and theoretically there's a Berry phase, okay? So I'm not the super theoretician, and I'm married to Stuart Parking, and he said, I don't believe this is total bullshit. Magnetization is 0, should be 0. And you have these domains, and you would see anyway nothing. So finally, we published without Stuart and Binhai. Binhai said, Stuart is right. Claudia and Kübler. So anyway, but luckily we were encouraged because Alan McDonald published something, and he's really a well-established theoretician, so we thought it's maybe not totally great. Anyway, experimentally, indeed, you see a large anomalous Hall effect in this material, and this was even from our Japanese colleagues, inspired by our theoretical paper published in Nature, because there's a large anomalous Hall effect in an antiferromagnet. This was already predicted by Nangosa, also that it should be possible, but this was the first experimental realization. And in this sense, I have to say sorry, Stuart, because he was in some sense right. The advantage of this material is there's a tiny moment because of this chiral antiferromagnetic structure, which allows us to have a handle on the domains and really see, if we apply magnetic field, we see this giant anomalous Hall effect, because it's a tiny, tiny, tiny moment, which Stuart always thought is dirty or dirt, but it's really related to this and anomalous Hall effect. So for me, it's interesting because it shows in magnetism, we have a lot to do, because there is no paper saying which magnetic materials are topological and which not. Is still missing. I think there's one paper from Ashen, it was a little bit, I don't know. Anyway, so here it's also, again, with crossing points related close to the Fermi energy, and probably wide points and the Fermi axe, which were not seen yet in this compound. So continuing with this Kogami lattice, so the people working on highly correlated systems, they like Kogami lattices because for frustration. And so after manganese 3 tin, you can imagine you think about iron 3 tin or cobalt 3 tin. Anyway, so the MIT team thought about iron 3 tin tin. So because there was a prediction that stannane is a nice quantum Hall effect system, spin Hall effect system, and iron 3 tin tin, if you want to say, is an iron 3 tin with stannane, iron 3 tin, and it's a single crystal, so it's a natural superstructure. What people use in film very often do very artificial. You grow here a single crystal, which was done from Czerkelsky, and so you measure, and this compound unfortunately has a spin in plane, but still it's a Dirac, massive Dirac fermion, and this was published this year in Nature as a ferromagnetic massive Dirac one. So we were working on a different compound because this compound is related also again, cobalt 3 tin sulfur 2, a little bit more, you know, I like even 3 elements, 4 elements, 5, but we had a discussion in the break, so why do we make so many different compounds? You know, we make so many different compounds because sometimes the elements are not good enough, and the binaries are not good enough, because iron 3 tin 2 is in plane. Here we have out of plane magnetization. If you want to have a quantum anomalous Hall effect, you might have to go with this. So we got very nice single crystals, and this is a calculation. You know, you have nice crossing points at the Fermi energy, and you have only 2 bands which cross at the Fermi energy, so it's really a semi-metal, different from all the other semi-metals in the literature, which are not semi-metal, they're all metals. Anyway, so it's even in this sense a half-metallic ferromagnet, because there's a much bigger band gap in the blue states compared to red states. And then if you apply a spin-orbit coupling and a magnetic field, so you can open up here again the lines to Y points, which are very close to the Fermi energy. So, and Jansson did this very nice calculation, and here was already clear that there is a large anomalous Hall effect. So we are going for the small things. We thought, let's look for an anomalous Hall effect. And, this is Jansson, he at the same time calculated nice Fermi axe. The Fermi axe are giant in this material, and even experimentally giant. This is 30% of the, I don't know what is the last interpretation you should discuss with Jansson about the Fermi axe. Anyway, the other thing is the referee said, look, you should really prove the chiral anomaly if you say you have a magnetic white semi-metal And indeed, you see exactly what was predicted, or is the theory set. You have, if the B field is perpendicular, you have a positive magnetoresistance. If the B field is in parallel, you have a negative magnetoresistance. But the magnetoresistance in this magnetic materials is not as giant as the non-magnetic. And here we find even an anomalous Hall angle around 20%. The only drawback in this material is like TC is only around 170 K, what is typical because this is a quasi 2D material, and all this 2D material you will see have not so super high TCs. But okay, for maybe trying, it's worse. And here again, it's also because the charge carrier concentration is very low in this material, the angle is so high. So then I said, let's, Jansson, can we make quantum anomalous Hall effect from this 2D material? And here you have also to ask Jansson, because he showed that you can indeed come from this 2D material, which is a Y-semi-metal, a magnetic one. If you do it in a 2D limit, it should have a quantum anomalous Hall effect. And he did the DFT calculation and sees really the edge state in this material theoretically. So we still have to confirm it experimentally. Okay. So we only have the bulk material. But we have now two nice systems also, one which has massive fermions, Dirac fermions, and one has the Y fermions in cobalt-3 in these materials, which shows you simply by thinking again from one material to the other we can go. There was no prediction. There was a prediction in-house, but not a theoretical prediction. But it's time to find more magnetic materials. And there was another paper published this week showing the 2D material iron-3 germanium tellurium-2, which has also a large anomalous Hall angle, up to 10%, which shows there may be more materials if we go to the 2D limit. If we make them as thin films, we might have a quantum anomalous Hall effect at higher temperatures than in doped bismuth selenide also. Okay. Good, I'm here at the end because this fermion is stored, and he will go back also to the spin Hall effect, I think, in his talk and tomorrow. And I thank you for your attention, and I'm ready to answer questions. Thank you.
Any questions? Anyone? I have a question myself. In the Heuslers, what is the largest magnetic moment that has been measured?
So in the largest magnetic moment is 6 μB for the 4 atoms in the unit cell. So it's quite large, but it's comparable with cobalt, so it's quite large. But we can make it also very small. So this is a good thing. I think it's maybe, yeah, also in tetragonal Heuslers, it's 6. No, it's not more than 6 in the fermion system, which have also quite large. But the nice thing is we can make them also small, so it's tunable. So in case if you, so this is a good thing. We can have large, and by counting the electrons, we can make them small or large, whatever you want. But the 6 μB is also in still half metallic, in a half metallic ferromagnet.
Can you go to well, semi-metals and explain again why you feel that they stabilize the Dirac Hall? Because you said something with this.
No, but I think if you have this half metallic, the good thing is of the Heuslers is if you have if you have many bands at the Fermi energy, you might have. So if you have a band structure, if you have band structures which have crossing points and you have time reversal symmetry broken, then it should be a Y, okay? But the nice thing is of the Heuslers, if you have half metal, if you assume spin, which you cannot do if you apply spin-orbit coupling, you know, and if you do a Dirac calculation, then the spin is bad quantum number, but you have a half metallic ferromagnet, which means you have a gap here, no states, and only states here. So you already have less spaghetti around the Fermi energy, you know. So therefore, they maybe are better. The system which are close, the families which have half metallic ferromagnets, which have, if you have no Dirac equation or so have a gap in one spin direction and some crossing bands, I think there's a high probability that you find a cross around the Fermi energy, and if you can dope them, and then you have even nice Y points, you know. So in the cobalt titanium tin, unfortunately it's here, so you have really to put a lot of electron in. But I think the good thing is it's time reversal symmetry is broken in this magnetic material, and crossing points are everywhere, you know, in the band structure. But I have the feeling you see really chiral anomaly and stuff if you have not a relative clean band structure, so if you not have too many bands. So, but it's a very good question, thank you.
In your violent Antiferromagnetic, in your Chiral one, you've got the measurement of the magnetic resistivity, or -1 in red, and you said that this is small.
Yeah. In this cobalt 3 tin, it's not so large as we have, for example, in mercury telluride or some other material. But this is because I think it's about, where's my, it's similar like in other systems where people measured in this magnetic system, they measured also here, for example, manganese 3 tin, they have a similar order of magnitude. You see the magnetoresistance is not like we have in niobium phosphide, we have a magnetoresistance of 100,000 or million, you know, in here. But because of the spins and the scattering, I assume we never get such a high magnetoresistance.
But the question is that is compatible with the quadratic magnetoresistance, or it is linear? I mean, the red one.
Yeah, but
in the left one.
Here they fit it, and it's B to the which? In which part?
Sorry, the previous one, in the B panel.
In the B panel.
Sorry,
I think I had the only.
Yeah. So you have a negative magnetoresistance.
Yeah, but
so
we fit this here to the positive magnetoresistance. The B square is related to the positive magnetoresistance.
Yeah, that's negative one.
Yeah.
If they are parallel.
Yeah.
So it's not, I mean, that's using the I, it's not strictly quadratic.
No, it's not quadratic here. Right.
But it's not linear.
No. But this is like, it's a very, so we by ourselves didn't want to put the chiral anomaly even in the paper, but we were forced from the referees because anyway, so we still think you have to first show uppers and so on, but okay, we don't know. So I think we might have to get better crystals, more optimized crystals and so on and so on. And so on. No.